right. So tell me a bit about indexed categories.
All right. Yeah, so we wanted to talk about categorical logic a little bit. So I thought I'd just go through the main canonical example, partly because I've prepared 0 minutes for this, so this is on the fly, so let's just stick with the easiest example and then maybe just like speculate about generalizations at the end.
Okay, sounds good.
Cool. All right, so there is a when we think about predicate logic, what are we dealing with? What are we like manipulating?
Well, one answer is predicates.
Yeah.
Okay.
Yeah. So what is a predicate?
So a predicate is a function from a set to prop, which is like prop is like the type of propositions.
Yeah. Yeah. So a predicate on a set A is a function. Want to pause?
Yeah, we can pause. Well, we won't pause, but we'll stitch it back together.
All
Predicate
right.
on a set A is a function.
It's just a function.
It's just a function.
A function from x to y. Is a function from A to, let's call it phi, from A to 2, also known as true, false.
Okay.
Right, because it's some property where we are evaluating each element of A and judging whether or not the property is satisfied.
Okay.
So, when we think about predicate logic, if we call this special set 2, or do you want to call it omega?
Let's call it omega.
Let's get fancy.
Yeah, let's get fancy.
This would also be known as prop in
Type theory.
fancy type theory and Haskell and stuff. And so when we think about predicate logic, it's really just about going from set theory and looking into this special object. So in category theory terms, that looking into is thinking about this Hom into omega. This is a functor from set op to something that sends a set A to the set of predicates.
Okay.
The set of predicates on it.
Okay. And would it send it to this category of posets?
Well, yeah, the poset of predicates.
Yeah, the poset of predicates.
Yeah. So there's lots of things we could write for this codomain.
Right. The category of posets lives in a lot of different spaces. Yeah.
Yeah. So I guess it's a little misleading to write this as an internal Hom. The thing that's going on is that omega has a lot of nice internal structure, even though it's a very simple set.
Sure.
What are like the things that we can do to omega?
Well, okay, so we have and.
Yeah.
And we have or.
Yeah.
And we have not in this case.
Mm-hmm.
And we have like implication.
Yeah. We can construct that from the others. Is that it? And some laws.
And some laws.
A bunch of laws. These are commutative monoids, and then you have like De Morgan laws and stuff.
Okay.
And what is this whole structure?
So I'm thinking Boolean algebra or some sort of algebra.
Yeah. Yeah. So we could say this goes from setup to bool.
It's terrible for any programmer. That's a terrible name.
Okay. Let's just call it. Let's call it.
Or BA. BA works.
Sure. Yeah.
Okay.
Balge is strange. I've never thought of that.
Why not? Balge?
Let's go for it. But it looks like B is a functor.
Okay,
And-
okay.
Yeah. Okay, yeah. So this is saying.
Oh, right. Algebra's over B. Yeah, okay.
Yeah. So this is saying that for any set, we get a Boolean algebra of predicates on it, and this is part of this nice general phenomenon we were talking about earlier this week, where given like a ring in some category or a group in some category, looking into it, Homs into it are also groups. There's this nice inheritance phenomenon.
Okay, and I guess the sort of interesting thing here is that, like, you know, this is like, these maps say that omega is an internal Boolean algebra, which in whatever category we're working with, but then when you take Homs into it, you get like a set Boolean algebra.
Yeah.
Which is kind of weird.
Yeah, it's nice.
It's kind of weird that, like, out of like, I think of an internal Boolean algebra as somehow like, oh yeah, no, that's not, like, there's some weird stuff going on. It's not quite a Boolean algebra, but like this fact that, oh, you can actually get a set based Boolean algebra. Whichever. Okay, cool.
Yeah, so it turns out the amazing fact that's like the starting point of categorical logic is that the whole system of predicate logic, that whole rich system that we're implicitly using all the time throughout math and throughout life, is somehow encapsulated by this functor and the nice properties that it has.
That's a big claim.
Isn't that?
That's a big claim. Right?
It's yeah.
All right.
It
All of predicate logic is this functor.
Yeah.
Okay.
So, I like this functor plus the properties that it satisfies.
So I have a quick question here. In like topos theory, you associate this functor with like the poset or Boolean algebra or whatever of subobjects. But it seems like you don't actually need to have that, like, this doesn't actually need to be a subobject classifier per se.
Yeah, I mean,
and like what is sort of the minimal structure that you need for this to like do something interesting?
Yeah.
Even when that's not a subobject classifier.
Yeah, so there's like a whole huge hierarchy of like, you know, the amount of structure you have versus the amount of structure of the internal language. This is just like the classic example, and it's more rich than some things. Like if you just had an arbitrary category with finite limits, then you would have nothing about any subobject classifier. You still have a functor. You still have this functor. Oh, why is this not? Oh. You still have a subobject functor from the category 2. In that case, it would be meet lattices.
Okay, because you can take pullback, but not. Oh, because there's no image factorizations.
Yeah.
Okay.
Yeah. So if C has
finite limits.
Yeah. We have this.
But
there's
then
all kinds of.
It's not representable.
Yeah.
Necessarily.
Exactly.
Okay.
Yeah, that's the thing that is special and powerful about toposes, is that there's this kind of like universe object like hiding in the category, and that's the fact that the subobject functor is representable is what lets you internalize the predicate logic.
Okay, but but you can still do like something with this subobject functor
Mm-hmm.
even though.
Yeah,
Okay.
that's true.
Can you give me like an example of like, yeah, like what fragment of logic can we interpret in a category with finite limits?
Yeah, that's a good question. I think it's called like Cartesian logic, and it's basically like you only have and. You have like and equals and
oh, equals.
and
Oh,
one.
because you have diagonals.
You have equalizers, so
Oh, you
you
have equalizers.
so it's not it's not a
Interesting.
trivial language. Yeah, I mean the language of finite limits is still useful.
Okay.
Yeah.
Cool.
Yeah, so really the bigger idea is that there's a whole hierarchy of categories with structure and languages between them. And we won't get into all this, but like that's what categorical logic is really about, is like there's a whole big correspondence in internal languages. And they all follow a similar story about these things that we're going to talk about called fibrations.
Okay.
So, so do you want to? Let's go ahead and just talk about what's nice about this functor first,
Sure.
and then we take the growth and deconstruction, and it like unions up all the images of this functor into one big category
Okay.
that sits over.
Okay, yeah, that would be
Set.
good to do explicitly.
Mhm.
Yeah.
But yeah, first, what's so nice about this functor that makes it somehow encapsulate predicate logic?
Do we want to rewrite it so that you can keep writing? Yeah.
Yeah, so the fact that each predicate lattice is a Boolean algebra gives you a lot,
Okay.
but there's more to predicate logic than that. So yeah, we have set.
Quickly.
Looking into here is this nice functor. But moreover, the thing that makes this really nice, maybe let's call it X and Y because that category is called BA. So let's just call this functor P for power set. The thing that's extra nice about this functor is that for every function, we get a triple adjunction. So by default, this this functor is sending f to preimage.
F to preimage. Yeah. Okay.
Right,
Sure.
because we have this special set, and what it's doing is like, what's the natural way to take predicates on y to predicates on x?
You just compose.
Just precompose, yeah.
Okay.
Yeah. So precomposition of predicates corresponds to preimage of subobjects. If we had taken the pullback here.
Okay. Okay. I see what you mean by preimage now. Okay.
Yeah. Yeah, so you can look at it either way. So this is what the functor is doing. But the nice thing is that for every one of those, there's a left and right adjoint. And what they turn out to be is a generalization. Well, no. Yeah. It's a generalization of existential and universal quantification.
So, the fact that we have these left and right adjoints is like somehow related to this idea that like Boolean algebra is like in order to talk about left and right adjoints, Boolean algebra has to be a two category.
Yes, exactly. Yeah.
And so in general, when you have this fibration, do you typically think about a fibration into a two category?
Yeah. So by default, we think about functors from COP to cat.
We think about functors from COP to cat. Okay.
Nice ones like that have this triple adjoint property.
And I see, and this sort of Boolean algebra is like a subcategory of cat.
Mm-hmm. Yeah.
Okay.
But it is nicer because, they're posets that have a ton of structure.
Okay, they have a ton of structure, and then we require the morphisms to preserve that structure.
Yeah. That is a good point. There's one little technical detail that, technically these don't preserve all the Boolean algebra structure.
What?
They don't, and that's an important thing.
You lied to me. You lied to me, Christian.
Yeah, it's a subtle point, because if you want to look at all three of these at the same time, the only thing they have in common is that they're functors of posets. The left one is a morphism of joined semilattices, and the right one's a morphism of mute semilattices. But the preimage is a morphism of Boolean algebra.
The preimage preserves limits and colimits because it has a right and left adjoint.
Yeah.
Exists preserves right adjoints preserve limits, left adjoints preserve colimits.
Yeah.
Colimits are joins.
Yeah.
So that preserves joins. That preserves meets.
Yeah.
Oh, and I guess
there exists blah 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 P or Q is the same as there exists P or there exists Q.
Oh, and I guess this kind of makes sense because, when you think of for all, that's kind of like a big and. And when you think of...
Exactly.
When you think of exists, it's like a big or.
Yeah.
Okay.
And that's really the heart of why these are left and right adjoints. That's really...
because...
We're going to go into more detail, but that's really all it is that...
Because exists is a big or.
Yeah.
And ors are colimits.
Yeah.
And left adjoints are constructed via colimits.
Exactly. Yeah.
Okay.
Yeah.
Whoa.
Okay. Yeah. So you know how colimit is left adjoint to the diagonal, like coproduct.
Colimit is left adjoint to the diagonal.
Like coproduct.
Let's pretend I don't know that.
Okay. Yeah.
It may be that I actually don't know that, but we'll let's pretend I don't know.
Okay.
Talk to me about that. So.
Yeah. So let's look at a specific function here. So, there's going to be two equivalent ways of looking at it. Do you want to go ahead and see how these are literally existential and universal, or do you want to
let's see how these are literally existential and universal.
Cool.
I think that would be interesting.
Yeah. So let's think about the case where our function is projection.
Mm-hmm.
Then tell me what preimage does.
What does preimage do?
You take a predicate on y, and then you are turning it into a predicate on x times y.
So it just sort of takes a subset here and crosses it with y.
Yeah. So a logician would call that weakening. So you take some phi of y from y to 2. What's the simplest way that you could turn this into a predicate from x times y to 2?
Yeah, you just compose with pi.
Yeah.
Okay.
Yeah. Weakening. You make x a dummy variable.
Okay.
Vacuously depending on x. So, can you see how this is in some ways a diagonal? In a certain way, every y, whether it was true or false, you're duplicating that and copying it for every x.
Okay. Sure.
So it's literally a diagonal.
Sure, because you can think of x cross y as like a coproduct of like
Exactly.
x-fold coproduct of y's,
Exactly.
and you're just sending
Yeah. Yeah, so like a diagonal. So let's think about what it means to have a left adjoint to this. So
wait. I feel like it would feel more like a diagonal if it was y to x to the y. Like the fact that it's x times y, like that feels less diagonally to me.
I mean, basically, yeah, I guess I just mean it's a copying. It's a big indexed copying of something.
Okay, fine.
Yeah. Yeah, yeah. So we don't have to use that word. So let's just work out what it means to have a left adjoint here. So what is the adjunction gonna say? There's an equivalence between.
There's an equivalence between there's an equivalence between wait, so okay, p y so we're thinking about predicates on x times y and predicates on y,
Yeah.
and we want the left adjunction. So okay, so let's
Let's
start on the
make up some predicate names. So let's call this phi, and let's call this psi.
do you mean element of?
Yeah, sorry. Thanks. Mm-hmm.
Okay, so we're gonna say that left adjoint is here. So we're gonna say that it like that dot exists
Mm-hmm.
exists sub pi, yeah.
Mm-hmm.
So exists sub pi of phi
Uh-huh.
is
Oh, you mean psi.
psi, yeah.
Mm-hmm.
Psi is less than or equal to phi,
Mm-hmm.
If and only if psi is less than or equal to p pi of phi.
Mm-hmm.
Okay.
Yeah, there's a lot of similar letters going on.
Yeah.
So what is this really saying? Like maybe we can write it more logically. So like you can think of the order in these Boolean algebras as entailment,
Okay.
which is just like a fancy way of saying implication. It's like the meta level of implication rather than the object
Can
level.
we write this in terms of contexts?
Yeah. Yeah.
Because like, yeah, I feel like it makes sense if you think about like phi as being in context x.
Yeah, we could write it like xy here. Well, yeah, so what we should really be writing, we could write it here as there exists psi is now a predicate on y.
Okay.
This implies phi of y, if and only if psi of xy implies this weakening of phi.
So this is saying like once we found some x that slots in here, then this is true, and this is true, like somehow for all x, right?
Yeah.
Because this doesn't depend on x.
Exactly.
So all we need to prove this is to find one x where that is true, and that's precisely the existence.
Exactly.
Okay.
Yeah. Yep. So it's really just a fancy way of saying that existential is a big or.
Okay.
And you have whoops. It's a big or overall x in x of phi x y implies, and we're just saying like the poset version of coproduct, because a map out of a coproduct is equivalent to just a bunch of maps out of each thing.
So, yes. Okay.
You can just make up some notation to mean like that the x is a dummy variable.
Okay. Yeah.
Yeah. So it's really just like exists is a big is indexed or
Sure.
Universal, and then the adjunction is literally just the universal property of coproduct, because coproduct in a poset is just joins.
Okay. Cool.
Yeah.
So how do these all? What's the fibration part, man?
Yeah. So now we're just saying, okay, we have this nice functor, where we have these adjoints, and how do we put it all together? That's what the growth and deconstruction is for. So index categories are nice. That's what these are called.
Indexed categories are functors into cat.
Yeah.
Okay.
Yeah, because you think like for every object in your category, you get a category.
Yeah.
That's why it's like an index category. But they're equivalent to these things called fibrations.
Yeah, we've been calling them fibrations the whole time, but yeah.
Yeah.
Bad abusive notation, but yeah, whatever.
Yeah. So are equivalent to indexed categories. And the correspondence is really just a big, nice categorification of two ways of thinking about indexed sets.
Okay.
So one way of thinking about an index set is just a function from a set to the whole category of sets.
A function from a set to the whole category of sets. Okay, so for each element of S, I'm getting a set.
Yeah.
Okay.
But that's kind of weird because like you're thinking about a function from a set to a gigantic class.
Yeah.
It's kind of a weird artificial thing. So the internal, more natural way of thinking about index sets is as functions.
Okay.
Where the fiber, the preimage over an element is the member of the family. So this one takes a little bit for your intuition to get used to, but it ends up being much better because it's internal to the category of sets. So it's like the category knows how to deal with it.
Yeah, and you don't have to worry about like, big old proper classes.
Yeah. Exactly. So, the correspondence between index categories and fibrations is just the categorification of that correspondence.
Okay.
So, it's just a little more complicated, but not much. So, like, if you wanted to go from this to this, what were you really doing for each? You were really just saying defining x to be the sum, right?
Sure.
Right. So in general, for categories, we're just going to take a certain colimit to like. It's still the same idea, is that we're just gluing a bunch of all the categories in the image together.
So I
into
feel like
one big
I feel like
category.
intermediate between indexed sets and indexed categories are like taking the category of elements of a pre-sheaf.
Mm-hmm. Yeah.
And what is like and so when you take the category of elements of a pre-sheaf, you get a category living like if you take the category of elements of a functor C up to set, then you get a category that's living over C. Is that right?
Mm-hmm.
What makes that category like come from a pre-sheaf and not a general functor to cat?
Yeah, it's just a distinction between these things called discrete fibrations versus like general fibrations.
Okay.
And the definition is just like you can recognize them when you take any object and you look at its fiber. How much structure does the fiber have? Is it just a set? Is it a poset? Is it a category?
Okay.
And you can just like tell.
And the fiber at an
pre-image.
object is the collection of objects that map to that object.
Yeah.
And morphisms that map to the identity on that object.
Exactly. Yes, that's
Okay.
that's an important point. Yeah. Yeah. But really, like the whole.
Okay, so you just look at that fiber and are like, is that a set or is that a poset? Okay, fine.
Yeah. But yeah, so the whole message of all this stuff is like, pre-image, is the natural way to index stuff, and indexing is everywhere in math.
Okay.
And fibrations are just the functors with well-behaved preimage. That's all that a fibration is.
Okay.
Because it's like by definition equivalent to an index category, and that's what's taking the preimage.
Sure.
A functor with well-behaved preimage, where well-behaved means pseudo-functorial. Or just functorial. So anyway, how does it work? How do we glue together these things? So we take our functor P from set up to Boolean algebras. Let's just take it to cat.
Okay.
Then how do we glue this together into one big category? It uses the integral sign because it's like a big sum, and it is literally a certain colimit.
Okay.
But it's kind of a fancy colimit. And you can think, okay, over every set X, I'm taking its power set PX.
Okay, is that X in set or X in set? Oh, X in set power set. Okay, fine.
Yeah. I mean, it's maybe you should write an op there. I don't know.
Okay.
It's not a big deal. So, how does it work? This is the category whose objects are pairs of X together with something in its power set.
Category is X and U in the power set. Okay.
I keep writing a subset of the power set. Yeah. And then morphisms. Do you wanna guess or?
Well, I'm guessing a morphism between X, U, and Y, V.
Mm-hmm.
Well, yeah, you have to have a morphism between X and Y
Mm-hmm.
that sends U to V with right. So I guess this goes in the opposite direction. So you could say
Mhm.
f, the preimage of v is u.
Yes, that is definitely. So you were saying equals, like the preimage of v actually equals u.
Yeah.
So the thing is, that would
Or the
That
the
would be for,
preimage
like,
of
a
v is included. U is included in the preimage of v.
yeah, exactly.
Okay.
Yeah, that's the generalization from like category of elements stuff to categories. Is that we don't want to require equalities. There's this
There's
extra
just- I
structure
see.
there, and
Okay.
all we want is a morphism from one thing to the other.
From
So-
one thing to the pullback of the other.
Yeah, exactly.
So we pull v back along f,
Yeah,
and then we take a morphism from u to
exactly.
that pullback.
Yeah. So we gotta like right now they can't relate. You gotta transfer one to the universe of the other. And then you require that u is contained in the preimage. What? Preimage of v.
Okay.
That's a morphism.
Okay. And so this is right because each because like p of y is a poset, like there either exists a morphism or there doesn't. But in general, for a fibration, you could say the data of the fibration is this morphism and that morphism.
Yes.
And there could be more than one choice.
Yes. Yeah. So, and then composition, you can infer it. It's going to be composition of the functions together with if u is contained in the preimage of v,
Right.
and v is
right,
contained
right,
in the preimage of x or
Of w.
w, then yeah.
Okay.
Yeah. Yeah. So that's how you glue together. I mean, you can just picture it. You have the world of sets, the world of categories. For every x, you get the Boolean algebra of predicates on it, or subsets, however you want to think about it. Blah, blah, blah. And for every function, you get these nice maps between. Blah, blah, blah. And all we're doing is taking a big union. So, and it just, when the image things are themselves categories, you need to do this pairing here, and this way of relating pairs.
Okay, I have one more question, and then we should probably break this so
Yep.
it's not too long.
Yep.
So this functor x goes to p of x, or this functor p, is nice because like at the beginning we said it sends f to a functor that has two adjoints.
Yes.
What does that correspond to in this like fibration language?
Yeah.
Like when you think of this as instead of a functor from set to cat, you think of this as a category living over set.
Yeah.
Where do those adjoints? What structure corresponds to those adjoints?
Yeah. Good question. So now the real structure that we're thinking about is this.
Yeah.
This is the fibration where the functor is just projection.
Mm-hmm.
And yeah, that's a good question. There's one way of saying it that's just like obviously equivalent. It's like over each morphism you have an adjunction between the fibers. There's a
you
nice
could say
way.
like yeah, exactly. Yeah, you could say like, well, take the functor corresponding this to cat and yeah.
But there's a nice way of looking at it as fibered sums and products.
Fibered sums.
So
and
there's like a
products.
completely internal way of saying what is a fibered sum and a fibered product.
I think of a fibered sum and fibered products as like pullback and.
Oh, that's a coincidence of terminology.
Okay.
Yeah. You could call it index sum and index product.
Okay,
or
index
something.
sum and index product. Okay.
Basically, yeah, so you can internalize this stuff by thinking about the two category of vibrations.
Okay.
Um,
The two category of vibrations. What?
and
Wait, so we're thinking about multiple vibrations? Okay, wait. What?
So like
okay,
an
the two category of
object.
vibrations. That's just like a subcategory of cat over set. Yeah? Like
it's a subcategory of like the arrow category of cat. So
okay,
it's just
yeah,
like
yeah.
yeah.
Oh.
So it's just like
oh,
nice.
Oh, so not just over sets.
No.
Like I see.
Yeah.
Okay. So
Yeah.
it's like an object is a vibration over any
Yeah.
base,
Mhm.
and then a morphism is a commuting triangle of vibration. Commuting square.
Yeah, yeah, and then there's two cells and stuff. It's a nice fancy thing that
Okay.
experts think about. Anyway, there like you can the formal way of looking at limits and colimits in cat through like certain kinds of adjunctions. You can do the same thing in this two category, and give a nice like big picture view about what the indexed version of sums and products looks like.
Oh, okay.
But it's still adjunctions in a certain kind of two category, in the same way that limits and colimits can be characterized as adjunctions.
All right. And to finish this off,
Mm-hmm.
if you had to summarize like I don't know, like one practical benefit of this vibration approach over the functor to cat, what would be like a cool tips and tricks style, like if you're trying to work with this functor, it's actually nicer to work with the vibration because this comes out much cleaner.
Yeah, good question. So why vibrations? Basically, just think about like these two perspectives for sets. This crazy way of thinking about families of sets versus this way. Nowadays, with like dependent type theory, people are seeing that this way is like totally essential to view families of sets as being morphisms in the category,
Okay.
as being completely internal. And the reason why that's important is so that you can have a pullback here, and just have it directly transfer one index set to another.
Okay.
Because it's like in the category rather than having to externalize it like this. It's basically like the same story for vibrations. I mean, I don't have enough experience with them yet to like really give like strong specific examples, but like in some sense, vibrations are like this huge categorification of index sets, which are the simplest kind of dependent
maybe
types.
one way of thinking about it is that it's all about like internalization. Like this is sort of like an more external definition that like depends on this external category set, and this is more like, I guess maybe one thing is that like, yeah, maybe in other categories, like if you're working in another two category, maybe this generalizes.
Definitely.
Okay.
Yeah. Yeah.
Neat.
So like one example is like when people think about um, index sets as dependent types, they're like the classic simple example of a dependent type where you say like, okay, for every little s, you get the type of stuff over it. Um, an element, a term of that dependent type is a section.
Oh, okay.
So that's the kind of thing that's like awkward or difficult to even phrase from this
Right.
perspective, but becomes very expressive from the index point of view. So like, you know, David Jazz is writing a whole book about sections of vibrations
Okay.
interpreted as dynamical systems. So I don't know much about the specifics of all this stuff, but it's very expressive.
So I like the sections picture. That's a
Yeah.
good. Is it okay? And then maybe I guess, yeah. What would just okay? Maybe and then we'll
section
close
of
with
that,
the.
yeah.
Maybe that'll be left to the reader.
Yeah.
Think about that. Think about that, people. What exactly is a section of that? It's probably meaningful in some way, but I don't know what it is. All right. That's a wrap.
Yeah.
Bye guys. See you next week.
Bye.
Or ish. I don't know. Next 2 weeks, something like that.